90%, that's good. And go there. And then somewhere I wrote down quality, where would it be?
Should be like 95-ish.
Yeah, it would be up in the 90s, I would guess. I know where I did it. Didn't do it down here, I know I didn't. I know I didn't do it down there. I don't see quality. Maybe I didn't figure quality for that one, so I guess I did not grab that piece of the puzzle right here. I'll have to find it, tell you what it is later. So I'm not wasting your time just looking at stuff. Let's see, what numbers, did anybody do it the not so correct way?
I put that way we did there, and I put it in rough cop, and I got like 93% quality for.
Now, okay, 93, yeah, that sounds like what quality should be. My eyes are just aren't, I know I calculated, but I just don't see it. Just don't see it right now. So yeah, I mean, that sounds good. And a quality above 90% is generally considered as you're okay. You're probably not going to hurt the last set of turbine blades, right? If you're in the 90s, right, on quality. If you're lower than that, you've got a really efficient turbine, okay? And you may be hurting the performance of those last set of blades. I don't guess we ever talked about this, but you know, if we've got a nozzle that is directing steam, right, to a set, that's not a very good blade, but, to a set of blades. So here's blades, not very good blades, but blades nonetheless, okay, right? So steam's coming in to a stationary set of nozzles, getting accelerated and redirected so that it hits this set of blades. These blades are on a wheel that can rotate, right? And there's an infinite number of them, right? Because they're on a wheel, keeps going around. Okay. What we want is a high velocity jet of steam that comes in, hits this blade, turns, goes the other way, causes a force, makes this thing move. If we have droplets, okay, if we have less than dry saturated steam, if we've got droplets. Now, what's the density of the droplets like compared to the density of the steam? 3 orders of magnitude different, right? You know, not 1 order of magnitude different. It's 3 orders of magnitude difference. It's like a lead bullet flying through the air, right? It's that kind of a density difference. And now, if you're shooting a rifle long distances, and there's a crosswind, does that crosswind influence your shot? Absolutely, right? If you're doing a 1/4 mile shot, how much does your bullet go downstream if you've got a 30 mile an hour crosswind? Well, I don't know, but it's not hundreds of feet. It's parts of an inch or maybe a couple of inches, right? It's in a 1/4 mile, right? The bullet just barely influenced. I mean, it's influenced, and it will absolutely destroy a sharpshooter's ability to hit a target, right, if you've got a crosswind. So it's important, but from the standpoint of really making that bullet turn, it's just not, right? What we're doing with this steam is we're really making it turn. We're making that steam, we're making it turn and accelerate. Go, let's go, right? Let's go faster. These bullets, nah, don't really want to, right? Not interested. in accelerating or turning, either one, okay? So what's gonna happen is these bullets, these droplets are gonna come out of this nozzle a whole lot slower than the steam, because they didn't accelerate. They go, go, go. Nah, it's kinda like you guys, nah, just not going, right? So what winds up happening is the steam comes out at high velocity, hits the blade right where we want it to, does what it's supposed to do. These droplets hit the back side of this blade. Now this blade hits the droplets, okay? Momentum exchange in the wrong direction, right? Hurts the efficiency of the turbine, right? Well, we want force, we want a great big huge force going that way, okay? These droplets, they're gonna hit the wrong side of the blade. They're gonna cause a force in the opposite direction. Not good for efficiency, right? A bad thing for efficiency. And these droplets, these blades are moving really fast. 3,600 RPM, most turbines are going to be spinning, most US turbines are going to be spinning at 3,600 revolutions per minute, because we've got 60 hertz electricity, right? 60 cycle electricity. And this is a big magnet spinning around, and we've got to make that stuff hit 60 cycles, 60 hertz, right? 3,600 RPMs, what these things are generally going to be spinning at, maybe 1,800, right? Some whole number, derivative of 3,600, right? Of 60 cycles per second. And so, there's pretty good velocity with these blades moving, and there's still significant velocity of the steam. There'll be a significant velocity difference between blade and droplet, and what will start happening is we'll blunt the ends of these blades, which means the steam that should be nicely flowing into these cavities now all of a sudden has an opportunity to blunt against a blade, which also negatively influences efficiency and life of the turbine. So, quality, important issue, important part of the puzzle. Yes, Nathaniel?
So it's like gas turbines, that they have to design the blades more for temperature, like since it gets super, super hot. With
Yep.
this one, are they designing more for like to be able to take more force on it and then like just stronger?
Absolutely. More force, more strength, more forgiveness in expansion. Okay, we want to make sure that we allow these turbines to move around a little, dance around thermally and mechanically, right? So we're going to be more forgiving there. It's interesting that for steam systems, in the same vein, the same idea, for steam systems, maximum temperature of steam is in the neighborhood of 1,000 degrees Fahrenheit. Remember, for gas turbines, our maximum temperatures were upwards of 2,900 degrees Fahrenheit. A lot higher temperature. Reason is, comparatively speaking, gas turbines are operating at lower pressure than steam turbines are. Okay, so we're doing higher and higher pressure on steam turbines. So we limit the temperature because the steels, the materials cannot handle these super high pressures with much temperature over 1,000 degrees Fahrenheit. Other questions? Good questions. Yeah, good. Any other questions? All right. So when these questions come up on the exam and you were watching your phone, you can blame yourself for not knowing these things. Let's see, what else was this? Cooling water. Cooling water flow, or cooling water requirements. We were looking exhaust blade velocity loss. That's good stuff, but we'll save that for another year, some other time. I don't know that I did the heat transfer to the condenser, did I? Mercy, what was I doing last night? Evidently not this. Longview turbine at Eastman. No. Mechanical engineering 371 turbine. Georgia Pacific TG3, no, not it either. All right, maybe I didn't do it. Well, so in my world, I had to come up if I had done this problem, I had to come up with the enthalpy of the steam leaving the turbine. That hours? No, that's the first one. What about this one? There we go, 600, 800. Or was it 850? Probably changed the number somewhere along the way. Yeah, so with this one, I got an isentropic efficiency of 66%. So I think we were 850, weren't we, today? Yeah, 850. Well, these are not the same numbers as what was going on, but working through finding enthalpy at the exit of the turbine, using the power generated by the turbine shaft, the equation we have here. Then you can know the enthalpy of the steam coming into the condenser, and you can know delta H for the condenser. And so we can, if we know enthalpy at the exit real, right, then heat transfer in the condenser is equal to mass flow rate of steam through the condenser times enthalpy entering minus enthalpy exiting, right? And so enthalpy entering is this HER, right? The enthalpy exiting the turbine real, and the enthalpy exiting the condenser is going to be H-sat liquid, otherwise known as HF at P condenser. Then that's got to equal mass flow rate of cooling water times specific heat, or sorry, not CP for the cooling water, times C, T exit minus T inlet of the cooling water. I probably got signs wrong. No, those signs will work, won't they? I think so. That'll, with a delta T of what, 10 or 20, right? A specific heat of 1, solve for the mass flow rate of cooling water. Questions or comments?
Question.
Yes, Keith.
Is roughly 3 million pound mass per hour a real number for chilled cooling water?
Yeah, it could be. What did I get back here? I got 10 million pounds an hour. A little different problem, right? A little different problem, but yeah, pretty close. Pretty close. Yeah.
That's a lot of water.
Yeah, a lot of water. Yeah. That's why you guys, John Sevier, remember the cooling tower? Oh man, mercy. Yeah, it's a huge amount of water.
Huge Niagara waterfall.
Yeah, it's a monster amount of water. Here's 2 homework problems. Two.
What the heck?
Determine the absolute minimum amount of power required to pump 1,000 pound mass an hour of water from atmospheric pressure to 100 psig. Determine the absolute maximum amount of power that can be developed by expanding the same 1,000 pounds an hour of saturated water vapor from 100 psig back to atmospheric pressure. So just a simple little fluid mechanics, pump it up, thermodynamics, turbine it down, right? Just do that, see what kind of numbers you get. And a more interesting homework problem. Simple steam power plant requires evaluation. System operates with the following conditions: boiler outlet pressure 1,000 psig, 750 degrees Fahrenheit, 100,000 pounds an hour of steam flow through the system. Turbine exit is 0 psig. That's the turbine exhaust pressure. Assume everything's working at the best efficiency it could work at, right? So really good efficiency, 100% efficiency. Tell me how much fuel you'd have to put in to do that. How much power would you produce? How much heat transfer in the condenser? How much pumping power? And the overall unit efficiency. And then, what if you increase the boiler discharge pressure to 1,100 psi? And then, what if you decreased the turbine pressure to negative 10 psi? What are those impacts, those effects? Class dismissed.
Could you explain again why you can't get the enthalpy at the exit with rev prompts?
Yep. So for this guy right here, if we say that P exit is 0, sorry, speed gauge, that's what we're going to do. Negative 14 pound force E squared. And if we've got a thermometer that measures T exit equals 90 degrees Fahrenheit, then it just so happens that 90 and negative 14 are saturated conditions. Okay. So